Welcome to a module on identity theft, or the methods and techniques for stealing user credentials from systems. Let's begin by attempting a classification. What subtypes can credential stealing attacks be divided into? We refer to authentication credentials and not passwords, since we are now aware that operating systems, except for poorly designed systems, don't store user passwords. The first type is an offline credential stealing attack. Having accessed or gathered some credentials, an attacker might attempt to recover a user's actual password from them. This sort of attack is very vicious and quite notorious. If you hear that the database of company X or Y has been leaked, don't expect it to contain any plain text passwords. These type of databases are obsolete now. The leaked files will instead contain credentials or hashes generated from passwords. There's still the risk, of course, that having obtained the credentials, an attacker can reverse a hash. We'll talk about how to do this in a minute. But attackers don't have to do it at all, since they have credentials that are capable of authenticating them in a system. Passwords are irrelevant in this scenario. What's important are the LN and the NT hashes and the TGT ticket. If an attacker has a TGT or a hash, user passwords are no longer a prerequisite. He can make good use of the credentials he got a hold of. The second class of credential stealing attacks are passive online attacks that intercept credentials sent over a network. After a successful interception, the credentials are used to obtain a user's password or to impersonate the user in a system. Interception is a time-consuming process that doesn't always go well. That's why the man-in-the-middle attacks or replay attacks are usually used to run it. We'll talk about one replay technique in particular soon. Active online attacks rely on cracking passwords. An attacker doesn't have to have any cryptographic resources. He only knows something about the user and will try to guess or determine that user's password. If this knowledge proves insufficient, the user, for example, has a secure password, it's very easy to detect and block an active online attack. An effective countermeasure in that case is to enforce locking an account after a limit of failed login attempts is reached. The fourth category of credential attacks are strictly social engineering attacks. Why would anyone want to lose a day's, a week's, or a month's time cracking a password if it's enough to politely ask a user to share it with you? How are offline attacks constructed? What methods are used? A brute force attack is one of the potential threats here. This is an exhaustive key attack that relies on checking all combinations of characters. As you remember from the previous module, a successful brute force attack on NT LAN manager protocol takes from 10 to the 20th power to 10 to the 600th power operations depending on the strength of a user's password. This would take a lot of processing. Dictionary attacks are at the other side of the scale. There's a list of potential or common passwords and each entry is checked one by one. This check doesn't take long. There's little computing here. Remember that an offline attack requires the possession of some cryptographic resource, such as an NT or a LAN manager hash. It's impossible, even today, to generate a list of all possible passwords and store it locally in the case of secure protocols. Possibly with LAN Manager, a good server would be able to store an exhaustive password database. Why did Microsoft decide to implement this protocol at all? 20 years ago, when Windows NT and Windows 95 operating systems were being developed, nobody assumed that the solutions then used would still be implemented in 2012. Even 10 years ago, hardware and software was evolving so fast that 2 new architectures were released in a year. A year-old computer was already outdated and unable to support many functionalities or run many applications. Nobody thought 20 years ago that the solutions then created will be in use for this length of time. The year 2000 problem was the perfect example of this. Many programmers simply did not expect their code to remain in use for systems for so long. Coming back to offline attacks, we already know that calculating all possible combinations consumes a lot of computational power, and that storing all calculated combinations is infeasible as it would require massive storage resources. Let's try to strike a balance. The trade-off is provided by rainbow tables developed by Philippe Oxlin. Instead of saving all possible hashes somewhere, you can only save some of them. What hashes should be selected, though? We don't know what would be the efficiency of a rainbow table. The trick is using a reduction function. This function should be as random as possible. We don't base here on some arcane knowledge of hash generation or on user data. We'd like to use a function that maps a hash to a corresponding password more or less randomly. The reduction function is the opposite of a hash function, such as the MD4, MD5, or SHA-1 functions. We save a first password in a rainbow table. Let's track a single chain. The first value is a password, followed by a function that generates the hash from the password. For example, a LAN manager or NT-LAN manager hash. Next, we have a reduction function that is used to recover a password from the hash. As we said, this is supposed to be random, so the extracted password will not be the same password that was first entered. We generate a hash from a newly created password, and next, using a second reduction function, we generate a password from the hash and so on. This creates a single rainbow table chain. Instead of saving all combinations into the table, we only save an endpoint. We save the starting password and the last computed hash. To increase the chance of all possible passwords being contained in a rainbow table, there has to be a lot of chains in it. We add a second reduction function to improve the odds. If each reduction function was displayed in a diagram in a different color, it would look like a rainbow. Hence the name, the rainbow table. We took the best of the previous attack techniques. We have some things pre-computed and saved. The first password and the last hash. But the data doesn't take too much space and can be stored on a standard hard disk. Now, computing is simply reversing individual chains by comparing a password being cracked against the values returned by transformations that reverse the direction of the arrows in the chart. If there's a match, we have found the password. If the values don't match, it seems that we're not successful and the password is not contained in the chain in the rainbow table. We had to apply some computing power and use up some storage, but overall, this solution looks extremely effective. Thank you.